let us begin and talk today about quite a few different topics. It's very fun. I don't think we're going to get through every single one today, but we'll get through a few of them. I'm excited to combine the ideas of logic and computer science because it's a very good idea they made this a critical thinking class. There's a lot of critical thought that goes on when you're programming. There's a lot of actual logic. So I want to teach you that formally now. Okay? So let me introduce you to formal logic. Okay? And logic is all about talking about ideas that are either true or false. Yes or no answers. Like, yes, this is true. No, it is not true. Therefore, it is false. Okay? So in order to, of course, talk about what things are true and what things are false, we have to define what it means to be true. That's super philosophical, so this is another philosophy class for the day. Let's go on into that. What in the world does it mean for something to be true? What is truth, even? There's a lot of different schools of thought, so we're going to have to visit a few, okay? So let's break down some terms first so that I can say them and we won't be confused about them. So the first one is called a statement, and this is short for logical statement. We're always talking about logic today right now, so this is a logical statement I'm defining to you. Logical statement. Logical statements, I guess. I'll abbreviate it like that. So a statement, also called a proposition, by the way, logical proposition, is just a sentence, like an English sentence, that can either be true or false, right? That's the main idea of logic in general. So we're talking about true and false things. A unit that could be true or false is called a statement or a proposition, okay? A statement is a sentence that can be true or false. You could also call that a proposition. One thing that English sentence, perhaps, that piece of code, cannot be is both true and false. Cannot be both, okay? Which is interesting to think about. So there are some sentences that are not statements, that are not propositions, because there are certain statements that are both true and false, or are neither true nor false, things like that. So here's one of them. This sentence is false, that quote. That is not a proposition, that is not a statement, because if you think about it, no matter which answer this could possibly be, it's not that. Let me prove that to you. So either that statement is true or false if it's supposed to be a proposition, right? In one of those universes, it should make sense, right? But I'm going to prove to you that it can't be a proposition because in neither universe it makes sense. So this is either true or false if it's a proposition. Let's see what happens if this sentence was true, right? If this is a true statement, then this sentence is false implies that, no, it was really not a true statement. If it was true, then it's false. Does that make sense? See how I followed that logic? Otherwise, okay, maybe that's just not what it should be. Maybe this sentence is false as a false proposition, a false statement. In that case, it was telling the truth, wasn't it? So if it was false, then it was true. So we have contradicted ourselves in both cases. This is a contradiction. Neither case really works. Contradiction. And so this is not a statement. It can neither be true nor false. It can't be any of the two. Okay? It's nothing. It's meaningless. Are there any questions about that? It's weird to think about on a Monday, I'm sure. But that is the idea of a statement. So, sadly, we've figured out something about the world that is the case, right? If the world were perfect, and it's not, given the previous bullet, we would like to be able to prove all true things and disprove all false things and know how to tell the difference and all that. But that is impossible. There are a lot of strong mathematical results that tell you that that is impossible. You cannot prove everything that's true. There's going to be some things that are unprovable yet true, depending on the system you're using to prove your stuff in. That's a very complicated topic. Think back to this moment if you ever go and get a PhD in math. This is me telling you about it right now. So, it would be nice to be able to do this, though, and a lot of times you can prove that things are true and disprove things that are false. So, maybe then, coming back to this idea of defining truth, maybe then the things that are true should be the things that we can prove, right? We can prove their truthness. Maybe that's how we should define what it means for something to be true. We've never really thought about that before. We've just kind of taken truth for granted. But now we have to think about it. Okay, so here is what the internet thinks are important theories of truth. And I will teach you a few of them today. This is definitely not my main area, so if you've taken a philosophy class, if you're a philosophy major, and I say something wrong, please correct me. That will help both of us out. Okay? So here are some theories of truth, and I'm going to try and explain them to you. Maybe you align with some of them, but not others. Okay? The first one is called correspondence theory. This is what the correspondence theorists believe. A statement S is true if and only if S corresponds to a fact. This is a fancy logical term, if and only if. You'll see that again. So the correspondence theorists think that something is true only if it's a fact, right? Fact. That's the main word here. And then we have to define fact, and I don't want to go there, so we're just going to leave it at that. You can look it up in the dictionary, but that's another rabbit hole that you could go down. But their idea is that true things and facts are things that you experience in real life, in reality, right? True things, to them, correspond with reality. So that's kind of like linking facts with another word. That's their definition of fact. It's reality, okay? So, like, maybe Sherlock Holmes was a correspondence theorist, yeah? He's got his little magnifying glass going around looking at the world, and everything that he sees, he can confirm, right? Oh, yes, the grass is green because I can go get my little magnifying glass, look at grass. Snow is white, right? Snow is white there, therefore, would be like a true statement, because you can go drive to where there is snow and observe that, yeah, usually the snow is white, right? So that's correspondence theory. That is one way that people believe that truth should be defined. Weird, huh? Any questions about that? Just a brain-melting moment, this first little subsection about truth. I haven't really thought about what it means for something to be true before, have we? I know I didn't. So that's correspondence theory. Here's a funny meme along those lines. This raccoon is a correspondence theorist. But there are other ideas. And let me teach some of those to you as well. Okay. The next one is called coherence theory. This is another definition of what it means to be true. There's actually a few different coherence theories, but we're going to use the most popular one. So to a coherence theorist, this is what they believe. A statement S is true because it matches other true things. So if you know some other thing to be true, you can look at that and build a knowledge universe of truth. Something like that. And so here is how a coherence theorist would prove that it's true that 2 plus 2 is 4, right? They're going to be like, okay, 2 plus 2 is 4. That's a true statement because, get rid of that, there we go. That's a true statement because I know what it means to be 2. I know what it means to be 4. I know what plus does to numbers. I know what equals does to numbers. And from that, it matches those true things that I understand about addition, about equality, about physical symbols of numbers. So therefore, from my knowledge, this statement makes sense. It's true. It follows, we say. Okay? So that's how a coherence theorist might look at the world. It's like, I know what the pieces are. I know how to put them together. And therefore, the bigger picture is true. I get it. Okay? It's all about breaking things down. Okay, that's coherence theory. Does that make sense? Please shout out if there's any questions or comments about this. It's a very philosophical set of slides right now. We're going to get through them slowly but surely. All right. There are other kinds of coherence theories, and they kind of are similar, like they match other things. It's all about matching one thing to some other thing that you understand. So another kind of coherence theory would be something like, a statement S is true because it matches the beliefs of the majority of people in my society. That's a way that a lot of people think, isn't it? Probably not the best way to think in a lot of cases. So that's coherence theory. Matching something to something else you know. Okay? Let us talk about deflationary theory. Just a bunch of weird words today. This one I understand the least, probably. So, also called redundancy theory. To these people, they don't even like the word truth in the first place. Deflationary theorists, they believe, you probably just shouldn't have said truth. Like, we don't even need that word. It's useless. You don't need to say 2 + 2 = 4 is true. You just say 2 + 2 = 4. We don't need to define truth because there's no need. We don't gain anything by having an extra term lying around. Just say equals. Something like that. Okay? It's not even worth trying to understand what truth is. They would prefer to not have this lecture right now. Okay? So, yeah, this kind of goes around the whole idea of what truth is. So some people don't believe in the idea of truth. It is a useless topic to them, and this is something we could maybe look up together if you would like, because I don't fully understand why someone would want to do this. But that's okay. We can leave that to the philosophers. That's deflationary theory. And then the last one is the last one that makes sense to me. So this is called pragmatic theory. Okay? This is the final one that I'm going to show you, theory of truth. There's plenty more, though, on the internet if you want to look them up. This is, to a pragmatic theorist, they say that a proposition is true, something they're trying to prove or disprove. But they say it's true if it is useful to believe that it is true. Isn't that interesting? If it's useful, then I think it's true. So again, it's all about utility. So John Stuart Mill maybe would have been a pragmatic theorist. And here's how they define it, like beliefs that lead to the best payoff, that are the best justification of our actions, that promote success. Those are the things that are true, according to the pragmatists. Okay? Interesting. So it's okay if it's like definably false, like you go outside and somebody tells you snow is green. That could be true to somebody if that's useful for them to believe it. Maybe. That kind of goes against some of these other theories, right? So here's a possible pragmatic truth. This is my way of motivating it to you, perhaps. So maybe a pragmatic truth would be something like, I think this is a true statement. I will definitely get COVID if I go to the party this weekend, so maybe I should stay home. Something like that. Maybe it's very unlikely that you're going to get COVID, but if you were to believe this, and maybe you have a family member with a weak immune system, maybe this is the best truth for you right now. Does that make sense? If you believe that's true, that might give you the best payoff for you and maybe your family members. Something along those lines is my best motivation that I can think of for this theory of truth. Any questions about this one? Very vague, or not vague, just weird little ideas. Weird philosophical ideas make your brain hurt. That's what this class is all about. Okay? So we're probably both confused. Having to think about redundancy theory again confuses me. But you're probably extra confused about what it means to be true. Like, maybe you're having an internal struggle at the moment. That's okay. Again, there isn't a right answer. Maybe you align with some of these views of truth and you just don't like some others. That's okay. What you believe is true does not have to be the same thing that I believe is true, or truth. All right, there's no right answer, but at least now you know how to look at the ideas. Maybe you think, like, I have some views that align with coherence theory. I have some views that align with correspondence theory. At least you have a name to attach them to now. That's all I wanted to give you. All right. Are you ready to move on to something completely different? Something a bit more computer sciencey, I would say. So we had to talk about truth to get here, though, but I think we're ready to talk about symbols. Let's do it. Let me make sure I know where we're going today. Okay. Yeah. Good. All right, let's talk about Boolean algebra. So George Boole coming up all over again, true and false, and truth tables. Okay, let's learn about those things. So the whole idea of programming, of formal logic, is that saying sentences and being like, this is either true or false, there are a lot of contradictions in a sentence. There's a lot of ambiguity as well, right? If you try to tell somebody something, a lot of times they can interpret your sentence, what you're thinking, in a completely different way, can't they? I'm sure you can think of some examples when that's happened in your life. And so wouldn't it be nice if there is a way we could write something and have it always mean the same thing to everyone, to get rid of any of those contradictions, to get rid of any of those ambiguities? That would be nice. Okay, so we don't like these. Wouldn't it be nice if we could formally specify our statements in a way that makes them all make sense to anybody who reads them? Okay? Here we go. So I'm going to try and motivate the topic by asking you a question first. So let's see if this works out. So here is a sentence. Here's two sentences that I'd like you to think about. Let's go to the, I'll stop attendance after we're done with this question. So please get your attendance in as well. Here's a I'm sorry. Here's a written nice question for you. Let me clear it out, because we're not writing code right now. Where did it go? There it went. There we go. All right, so here's my my questions for you. So you go to a restaurant or you go to a cafe, and the waiter asks you, "Would you like cream or sugar?" Okay, that's one sentence. And then you're at home, and you're still a child, and your mom says that you can have a cookie or ice cream for dessert. Okay, so as a peer instruction group, get together with the people nearby, introduce yourself, say hi, and discuss the difference between those two ors. It's the same word in two different sentences, but I think it means a little bit different things in each sentence, doesn't it? So talk to your peers about that. Write down the differences, as many as you can think of, between this or and this or. Okay, so these two. Any questions about the question? All right, I'll give you like 2 or 3 minutes. Have fun with this. English sucks, doesn't it? Take another minute. Alright, that is my timer. Let's take a look at what we're thinking. Yeah, cream or sugar, you can pick both. Open-ended statement. Open-ended statement. When mom asks, it's an ultimatum. Yeah, kind of. You get one or the other, right? When you're asked, it's freedom of choice. Yeah, you can pick both. So you can have cream and sugar, couldn't you? That's exactly right. First or is asking whether you want the cream and or the sugar, making both options a possible response. The second or allows you to only answer one choice or the other. Very good. I think if I keep reading these, they will be along the same lines. That's exactly what I was trying to get at. Okay? So, first or, you're a paying customer. You can have both, right? Second or, mom will not let you have both. Do we all see that? Alright, so this is why we don't want to use English when we're formally specifying things in a logical way. We would like to instead use some form of math. Okay, so let me teach you that math. There are symbols that we will learn first, just combining symbols. The first symbol is called or, inclusive or. By the way, there's two kinds of or because we've just discovered there are two kinds of or. So we're going to differentiate them by having two different symbols for them. Okay, this first one's called inclusive or. This will make sense when I tell you the next one as well. So the symbol for that in logic is this V-looking thing. You put two things on each side. Okay? So let me first explain the truth table, and then I'll show you the symbol in action. So this is what's called a truth table, by the way. When I teach you this logical thing, this or, this inclusive or, I need to show you what happens depending on all the different outcomes. So you can or together two things, and so here are all the possibilities of the two things, A and B. So pretend that A is cream and B is sugar or something. And here is the result in this column of oring together A and B if they're both true. If one's true, the other's false. If one's false, the other's true. If they're both false. So it's trying all the possibilities and showing you the answer. So this is cream or sugar. And you write A or B as a little V thing. B, it's called like a wedge operator. So I would write this as in logic as cream or sign sugar. Okay? So that's the symbols. And here's the idea. This is a true statement in any of these cases. We say that A or B is true for inclusive or in any of these three cases. Okay? If they're both true, like you can, like these are the options that you can pick, right? Do you want cream and sugar? Sure. You want cream, just cream, no sugar, or no cream, just sugar. So this would be something like the truth value of the sentence, I had cream or sugar. Inclusive or. So, yeah, I'll get to this in just a second, but let's show how this makes sense. So let's say that this column is representing all the cases where you would say something like, I had cream or sugar with inclusive or. So it's possible you had both, right? If cream was true and sugar was true, then A or B is still true, right? You could have had both with that or, the inclusive or. It's possible that you had cream but no sugar. That's still correct to say this. It's still true to combine it like that, right? And then finally, maybe you had no cream and but sugar. Then it would be still a true statement to say I had cream or sugar, right? So you could have one, the other, or both. And that is called inclusive or. The one time you're lying is if you had neither, right? That's the one thing that makes this statement false. If both sides of the or are false, okay? So eventually we're going to want to prove things like this. Like, you tell me this, and based on previous information, tell me if this is a true or false statement, this cream or sugar, this A or B. So to prove that A or B is a true statement, you have to show that one or the other are true. A is true, or B is true, or both are true. Because that'll lead you to any of these three cases. Do you see how I'm reading that? We like the true cases. That's what it means to be true. That's how we prove something is true. The one case when it's false is when you lied. You had neither the first thing nor the second thing. Okay? So that is inclusive OR. You can have one, the other, or both, and the statement is still true. Any last questions about that one? That's inclusive OR. That's the waiter's OR. The other kind of OR, we give a separate symbol so that it's non-ambiguous. This is called exclusive OR, or XOR for short. Its symbol is, I won't use parentheses this time, it is a plus sign with a circle through it. That's how you do it. And some people just abbreviate it to XOR by itself. Okay? So here is the exclusive OR operation. Okay? Think of A as having a cookie and B as having ice cream. And then this is their combination, their exclusive OR. Cookie XOR ice cream. So notice that this is only ever true, A XOR B, if one is true and the other is false. It's only one or the other. Exactly one of the two options is true. Does that make sense? That's you had a cookie but no ice cream, or you had ice cream but no cookie, then that's what mom meant, right? That's the truth. Otherwise, you're not allowed to have both, right? You can't both have ice cream and a cookie. Then it wasn't exclusive. Or, it's still the same down here. If you had neither, it was still false, right? You're supposed to have one but not the other. Not both, but also not neither. Okay? So when you're thinking about falsehood, this is going to be a pattern for the day, if this is not making enough sense yet. You want to think about a statement and somebody lying to you. Think about false as a lie. Think about false as, I don't know, as if someone was lying. So if a statement is false, that means somebody was lying to you. So mom is saying you can have an ice cream or cookie, and mom is claiming that's a true statement. So it was a true statement if you ended up with one of these cases, right? One or the other. Mom was lying to you if you ended up with neither, but mom was also lying to you if you ended up with both, right? Because she should have used inclusive OR in that case. Okay, that's the one difference, this little bit. It's true there, false here. If you want to prove that an exclusive OR is true, A XOR B, you need to show that you have A or B, one or the other, but never both. Okay, that's how you would prove that you're in the true case, and the true case alone, for exclusive OR. Okay? Any questions about that? Once we get into symbol land, it looks a bit scary, but with enough examples, I promise it'll make more sense. We still doing okay? So think about false as if someone's lying to you. I think that's very helpful. Okay? Well, let's keep on trucking. Let's talk about and now. And actually corresponds to the and in English, luckily. The symbol for and is this thing. A little wedge thing. And so I would write it like this. A and B. Okay? So here's my example and statement. Let's say like the waiter says we have cream and sugar. And sugar. Okay. This is an A and B statement where A is like cream and B is sugar. And the and is claiming that you have both at the same time, right? They're anded together. So in order for an and to be true, you can only be in this one case, right? A better be true, B better be true. That's the only thing that makes their combination, their and, to be true. Okay? So to prove that A and B is true, you have to prove that you have A and B at the same time. Okay? So the waiter's lying to you. Flip side of this, the waiter's lying to you if they don't have any sugar, but they do have cream, right? Because they said they had cream and sugar, right? The waiter's lying to you, you're in the false case, if there was no cream, but there is sugar. Still, the waiter said, we have cream and sugar. You're supposed to only be in this one case, right? And of course, the waiter was lying if they have none of them, none of the two, right? That's not too bad. That's very Englishy. That's the only way to make it true. It's the only way to be a true statement is if you had both at the same time. Are you good with that one? That's definitely easier than the ors, I would say. All right, the final one that I want to talk about is not. Not just takes one thing, and it does what's called negates it. So it's negation is the process. Not is the operation. The operator looks like this. It's a little sideways flipped L kind of thing. And what negation does is it flips the true to false and the false to true. So you can think of the symbol as like a diving board that somebody's about to jump off of and do a flip. How about that? That can be your mnemonic. So the not A is the opposite of A. So if you have A, then the negation of A, if it's true, is false, right? You just flip it. True becomes false, false becomes true. So the only way to prove that not A is true is that you show that A itself is false, because that was the only case that would make it true. You see how it gets flipped like that? So the only way that this is a true statement, we don't have cream, sorry, we're out, is if you go back to the truth table and look it up. So this is the negation of having cream, right? So cream better be false in order for we don't have cream, which is not cream, I guess, to be true. Do you get that?
Those are just standard writing symbols, but not keyboard ones, right?
Yeah, it's hard to type these things.
I thought the not was an exclamation point.
In programming languages, yes. In formal logic, it looks like this. Yeah, just like in programming languages, the and is like some ampersands as well. So we pick different symbols, but this is what the logicians think is the right thing to use if they're like publishing a book. Yeah. Any other questions? So not shouldn't be too bad, right? You just take what you had and you negate it. False becomes true. False becomes true, yeah, and true becomes false. Either way. And here's a very cool idea, and something that leads us into how to make a computer, is you can express any truth table, no matter what, with some combination of and, inclusive or, and not. You just need these three. You don't need any others. So if you had some weird looking thing that you're not sure, some cloud, you have a bunch of inputs, maybe A, B, C, D, dot, 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 and you're trying to figure out what to put in here to make it say true up here, false down here, false down here, true here, false here, true here, blah, blah, blah. What is this logical statement? You can create this outcome with some combination, always, of your inputs and or a not. No matter what. Always possible. That's pretty cool. And so this will lead us to circuits and how to build computers. Because essentially, all computers are doing are pushing around trues and falses to do math, among other things. Okay? So, let me prove this to you. Let me show this to you. I'm going to give you the answer to this next question, actually, but I want you to work as a group to do the rest, to fill in the truth table. Okay? Here is the idea. I'm going to show you how to make exclusive OR using and, or, and not. You do not need exclusive OR by itself. You can always create it from the three building blocks. These three are building blocks. Okay? Exclusive OR can be created as a combination of and, or, and not. Let me show this to you. So A exclusive OR B is equivalent to, logically, it's equivalent to not A and B ORed with A and not B. So here's me using the symbols all right next to each other. Hopefully you can read that. That is quite nice. A exclusive OR B, it's really just this. You didn't need an extra symbol if you didn't want one. So I would like you to fill in this truth table. Let me get you started though. Because that'll prove that they are equivalent, right? So here's A, B. Let me try and draw the best line that I can. Whee! I think we're probably going to need all the room. Oh no, I want to stop it there. A, B, and then we want to eventually make, way over here, this thing. So how do we build the truth table for whatever that is? Well, we need to figure out what not A is, what not B is. We need to combine these with ands, and then we need to OR them together. So let's build all the intermediate terms. Okay, so we need not A, we need not B, we need, now that we have not A, we can AND together not A and B. Now that we have not B, we can AND together A and not B. So these are all different columns that I want you to fill in. That one. And then we can finally take these two and OR them together and look at the output. So we can have not A and B ORed with A and not B. Okay? So here's the standard order for the first variables. True, true, false, false, true, false, false. And here's what you're going to do for every column here. For not A, for example, you're going to fill this in by looking at the A column and negating it. So true becomes false. True becomes false again. False becomes true. False becomes true. See how I just filled that in? You're going to do the same for all of these. And eventually you're going to get here, once you have all your intermediate stuff done, and it's going to look the same as the exclusive OR's truth table. And that proves that it was the same symbol. Okay? So, just in case we forgot and OR, I think not is easy enough. Here's inclusive OR's truth table. I'll put it on the same slide while you work. Inclusive OR. I'll put it up here. And then here is AND. So I'll give you a few minutes to try this out, but I want you to fill in this table. Prove that it is true that this long thing is equivalent to exclusive OR. Okay? So do you all know what we need to do now? It's a bit of symbol pushing, but I'll only make you do it just this once. It's a very good thing to learn the symbols that we just learned with. Okay? So take a few minutes, help each other, and fill out the rest of this table, please. Let's see how we're doing on time. Tell me if you have any questions. accidentally clicked. There you go. Where am I trying to get to? Take one more minute and then I'll do it with you. Alright, that's my timer. We will get faster at this with more practice, but let me show you how fast you will be one day and you can compare. You know what the answer should be, right? Because it's supposed to be the exclusive or it's supposed to be false, true, true, false, right? That's how you can check your answer. So B, let's just flip this. True, false becomes false, true, true. So now we have not A and B. So here's the not A, here's the B. I'm going to AND them together. It's only ever true if they're both true, right? It's false otherwise. So this is the only true case for not A and B, isn't it? The rest are false. Then, let's see here. A and not B, that's this one. This is why we did it intermediate stuff. It's only true if they're both true, right? So this is true, and I think that's the only time they're both true. So that is this, and this. Only true there. Okay? And then to OR them together, it's now we have this thing and this thing. We need to OR them together. The OR is true if one of them is true or both, right? So here is one of them's true. Here's another one of them is true. For these, it's false, 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 still false, right? You have neither cream nor sugar. False, true, 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 false. Any questions about that? Because we have just proven that this is exactly the same as A exclusive OR B. Boop. Because that is supposed to be false, true, true, false. You didn't need the extra symbol. Just use and or and not. These are all equivalent. Okay? The truth tables line up. So that is a logical proof using a truth table. Any questions about that? Definitely come back and study this. Alright. There are some others that I don't really care about you memorizing, but I want to tell you about them because maybe you've heard about CPUs before. They've got a lot of NANDs on them. NAND gates. You've heard that. There are some other cool looking operators that are extra nice if you want to build a CPU. So here is a NAND B. That's an operation that's just equivalent to not A and B. So do A and B first, then negate that, flip them all. There's also NOR. That's do A or B first and then negate that, flip them. I told you that you can make any truth table with and, inclusive or, and not. And the fancy word for that is functionally complete. Functionally complete, okay? So all of those three operators together are functionally complete. NAND and NOR are even better. NAND just by itself can make any truth table. NAND itself is functionally complete. Same for NOR. NOR by itself can make any truth table. Just some combination of a bunch of NORs and parentheses. That's crazy. But this is really nice if you're going to build a computer. You need to make a bunch of truth tables at the end of the day, and you just want to build one kind of chip a bunch of times. So it's cheaper to just use NAND all over the place, and that's what CPUs like to use. You've heard of that before. Any questions about that? This is not something I want you to memorize, just food for thought. All right. Yeah, let's keep going then. So here is an English sentence that we would like to parse because there is some logic behind it, and we would like $20. So here's like Dad tells us, I will give you $20 if you clean the bathroom and, in parentheses, mow the lawn or do the dishes. So the or is attached to both of these. I tried to use parentheses to make it as unambiguous as possible. But here's a statement that we could try and prove or disprove, right? So you can call clean the bathroom A, you can call mow the lawn B, do the dishes C. This is essentially, we're getting $20 if A and B or C is true, yeah? And we would like to figure out the minimal amount of work that we could do to get $20, right? Because we are human. So under what conditions are you guaranteed to get $20? So what we're going to do is, of course, build a truth table. So let's make a truth table for this formula. Again, we have A, B, C, and the formula is A and B or C. Now, let me show you all the possibilities. A, B, C. We would like to AND this, AND A with B or C, so we need a separate section for B or C. And then we can finally AND A with whatever we get there. Okay, B or C. So I think that'll make our truth table. This one's a bit long because we have 3 variables. So we have 8 possible outcomes for A, B, and C. And the trick for filling out this quickly, all the possibilities for the variables, is the rightmost variable. You go true, false, true, false, true, false, true, false, until you run out of options. Because there's 3, it should be 2 to the 3, so 8 options total. And then for B, you say true, true. It stays longer on the true. True, true, false, false. True, true, false, false. Every 2, it changes. False, false. And then for A, it changes even less often. Every 4, it changes. So true, 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 true. False, 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 false. This is a standard way of filling out a truth table. It doesn't really matter as long as you have all the cases. That's an easy way to get all the cases. And then we'll do B or C. Let's see all the times that one is true or one or both. So that's true, false or true is true. This one's false because they're both false. And then there's a true, 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 true. This one is the only one where it's false because they're both false. Yeah. So true, 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 false. Then we would like to AND this with this to get the final answer. Yeah. So AND it with A. If you know your truth tables, you can very quickly figure out that you're never going to get true if you're down here. So you don't even need to worry about trying to AND this with this. It's always false, right? Only up here do we get something nice. So, because an AND is only true if both sides are true, right? So it looks like those are true, and then we look here and we see, oh, these 3. These are our 3 money makers, okay? So it's true, 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 and then the rest is false. So here are the 3 ways that we could have got $20. Either we cleaned the bathroom and we mowed the lawn and we did the dishes, or we cleaned the bathroom and we mowed the lawn, but we did not do the dishes. That's okay because we could have done one or the other. Still getting $20. And then finally, we got $20 if we cleaned the bathroom, did not mow the lawn, but we did do the dishes, right? And you can kind of read that from the sentence as well. Like you're forced to clean the bathroom because there's an and connecting it. And then you got to do one or the other. Okay? But if you have a complicated statement, you can spell it out in logic and see all the different ways that it could have been true. Okay? Any questions about that? It's kind of useful. You can see how that could become useful with a more complicated statement. You good with that? All right. Now I have a complicated example for you. Please create a truth table for the formula A and B or B and not C. So I'll get you started again. Honestly, I don't know if we have a lot of time. Maybe I'll do it with you, actually. Let's race each other. So I'll be very slow, purposefully, and see if you can fill it in faster than me. I'll get you started with the A, B, and C. This has got to be true, false, true, false, true, false, true, false. This one stays true a bit longer, twice as long. True, true, false, false. True, true, false, false. This is an easy way to get all the options. This one is true twice as long as the previous one. True, 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 false, 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 false. If you know binary, this is counting up in binary. Let's see here. And then we need to get out all of these. So this is eventually, we need A and B or B and not C. So we need like this one first. We need A and B. You know what that is, so we can combine it later. Then we need B and not C. So we need not C, right? Not C, so we can AND it with B. Make it B and not C. And then finally, we have all our pieces. We have the B and not C, we have the A and the B, and we can OR them together, right? So there's our A and B, or B and not C. Okay? So I'll give you like a minute head start, and then I'll start doing it, okay? Try to do it yourself. And help each other if you have any questions. Let me remind myself that this is a good idea. Insert text box. So we gotta complete this table. When is it true? That's usually what we care about. All right, that's a minute. Now I'm going to start talking out loud. Well, you can keep working. That's totally fine. You can check your answer with me at the end. So I like to do as little work as possible. So I'm going to search for tricks when I'm doing A and B and everything else, right? So it's true here. It's true here. It's going to be false when one of them is false, so it'll be false here. And what do you know? A is false all the way down here. So it looks like it's only true in the first two. That's nice. That's saving me some thought. I don't have time to think. Not C is just flip everything. So instead of true false a bunch of times, it's false true a bunch of times. And then B and not C. So I have the not C and I have my B. This is looking pretty ugly. What's the best way to do this? I guess you gotta just read it off. True and false, that's false. True and true, that is true, because they're both true. False, one of them's false, it's false. One of them's false. This one's false, so you're kind of guaranteed for it to be false here and here, if I'm looking at not C. And then, it looks like B is false here, but true here. So we'll keep those along. Okay? Looks like it's true here and here. And then finally, I have my two pieces. I have this piece, and I can OR them together. It's true if one of them is true. So automatically true for the first two. And then this A and B stops helping at that point. It's false everywhere else. So it's only ever going to be true if it's true here, right? So that's that one. The rest are going to be false because they're both false. So it looks like it's only true in these three cases. If A, B, and C are all true, if A and B are true but C is false, or if just B by itself is true. Okay, those are your three ways to make this true. And you could imagine this was some complicated thing that you really cared about. Maybe there's money involved again. Are there any questions about that? Did my explanation make sense? It is a lot of symbol pushing, but you're going to get used to that with experience. Is that all right? Maybe we'll study this after class. All right, because I want to finally tell you like the whole point of all this. Like, why are we learning truth tables? Why does this have anything to do with computer science? Like, it's cool, it's logical, I like that, but let's make this happen. So logic gates and circuits. This is where we're going. To build a computer, it's really just a bunch of ands, ors, and nots to get the final output that you care about, to like add numbers, to multiply numbers, to do complicated processes. It's just a bunch of and, ors, and nots. It's really cool. I have to take CSCI 45 to get there, but I'm going to give you a sneak peek, okay? How does this apply to computers? That's the question I'm going to try and answer for you now. So here are our logic gates. We're going to build diagrams like this, and they are going to perform our logical operations. And this is how we're going to perform computation eventually. So here are some diagrams, and the idea is, like, you read them from left to right. Like, here's A and B coming in along the wire to what's called an AND gate. I've named them. This is an AND gate, a NOT gate, a NOR gate, all those things. I only really care about you memorizing these ones, and or not. But then coming out of the wire, this is A and B. It, like, performs the operation inside of this box, kind of thing. Okay? And so it's taking in electrical signals. We can use transistors to make these logic gates. So 1 is true, and 0 is false, right? Also, you can think of true as high voltage if you're an engineer. That's what 1 really is, voltage. And false is also low voltage. However you want to think about it. But it's just, if you plug in true and true, it's going to send out along this wire true. Otherwise, it's going to be false, right? It's performing the AND operation. The NOT gate is sometimes called an inverter. You send in A along the wire, it sends out not A along its output. Okay? You can think of the dot as doing the negation. That'll help you read the NOR and the NAND. But here is the AND gate. It looks like the little bullet in Super Mario. And then the OR is curvy. It's got the curves on the sides. That's how you can remember. And it kind of like juts inward. It's a bit different from the AND. And this performs the OR operation. And then here are the other ones that I don't really care about you memorizing. But exclusive OR kind of looks like OR. It's got an extra line there. And NAND and NOR kind of makes sense because they do the OR first and the AND first and then the NOT. Because it is supposed to kind of be thought about being done from left to right. If you take the little dot to do the inversion process. Okay, so those are the gates. And now, if we have some nice formula that we care about getting the output for, making a computer that performs this operation, we're going to combine the gates. Okay, so let me show this to you. Let's create not A and B or C and not D. And so we have 4 wires at the beginning of time. We're going to use these gates for them. We have 4 wires. We got A, we got B, we've got C, we've got D, and then here's how it works. We need to create not A so we can AND it with B, right? So the very first thing happening to A should be being negated. Inversion. That's this gate. Not gate. So now we have not A coming along that wire to the output. We're going to chain that eventually. We would like to AND it with B, right? So we'll take B, and we'll take the not A, And we'll wire it up into an AND gate. Boop. That's this one. And then coming out along this wire is going to be not A and B. Yeah. We're going to do that for all of these now. So we're going to take C and not D. So I need not D first. So let's negate that. So I have not D. And I need to AND it with C. So I'll bring these wires together with an AND gate. Let's try and draw that nice for you. And so now coming out of here is C and not D. Okay? And then finally I have these two pieces. I need to OR them together. So I'll use an OR gate. That's the curvier version. Boop. And so then finally coming along this output wire is not A and B ORed with C and not D. And then you send this along to whatever needs to use it. Like maybe the user's screen or something. Who knows? A little blinking light on the outside of the computer. Any questions about that? I'm not asking you to come up with, hey, is it true or false? But I'm asking you to build the circuit to compute this logical thing. Any questions about how this works? Let's build them up, send the inputs to the outputs. Because here's your pretty picture, and I want you to try. This is bringing us full circle now. And then we'll see if we have a little bit of time left for binary. I don't think we have much. But take like, I don't know, 2 or 3 minutes and make the diagram now for this one. B or not C and not A and D. Use the parentheses as your guide, like you got to get this one first and then this one and then AND them together, things like that. So try to help each other make the circuit for this one. Give me 3 minutes and then I'll do it. So how would you wire up stuff to compute this answer? How would you executive decision to stop there, if we can, after I introduce binary. One more minute. Is this big enough to see here? I'll make it a little bit bigger. Again, you'll need wires for the inputs. Those are A, B, C, and D. That's where they begin. All right. So let's take a look. Let's see how we're doing here. We need 4 inputs, A, B, C, and D. And, well, we need to do B or not C. So we got B. We need to negate C. We need to OR them together, right? With, like, let me try and make this a bit cleaner. Boop. With an OR operator, an OR gate. So coming along this wire is B or not C, right? And then we need to take not A and D. There's no, I guess you could have drawn these in different orders. Make it look a little bit cleaner, but we need to AND A and not A and D. So we negate A, we got to bring it along here to D. One way that people, like engineers, like to draw these to just show that, you know, they're not passing through, they're not touching, is like they kind of hop over, and then you AND them together. So this is showing not A and D. And then finally we want to AND together those last results. So there's no easy way to draw this in the way that I chose to do it, but there is where the answer would come out. Okay, is that what we got? Are there any questions about that? All right, because in the last few minutes, 2 minutes of class, I would like to teach you the beginnings of binary, because that's how things are stored inside of our computers. I've shown you about single trues and falses, but let's build numbers using trues and falses. Okay, that's the last piece of the puzzle here. So binary is the whole ones and zeros thing. That is going to give us the full power of a computer to represent numbers and do arithmetic and things like that. So 1 is true, 0 is false. Binary is made up of 1s and 0s. And our computers are completely formed of logic gates. So all that is inside of this computer is a bunch of and, ors, and nots. And maybe a little clock sending a signal so that it can move information along. That's it. 1 is true, 0 is false, and we just do a bunch of stuff with wires. Okay? Everything in our computer is stored using just a bunch of 1s and 0s in some fancy way. Okay? So because of that, we better learn binary. We better learn how the computer does its thinking, okay? Because we as humans, we think in what's called base 10. That's decimal, okay? Another word for that is decimal. Our numbers, the reason it's called base 10 is because our numbers are made up of the following digits. 0, 1, 2, all the way to 9. That's 10 digits total, isn't it? 10 digits. That's why we call it base 10. The reason we think we use that is because we have 10 fingers. Maybe if you were in the Simpsons land, they would use base 8. But the reason it's base 10 is you have 10 digits, and then if you try to add 1 to 9, you run out of place, right? You have to add a new digit. Add the tens place. And I'm going to be talking about different bases, so when I talk about a number, like 1, 0 in binary is not 1, 0 in decimal, so I'm going to differentiate it with this subscript. This is 1, 0 in base 10. That's really the 10 that we know, okay? This is 123 in base 10. Not some other base, okay? Binary is kind of cool because it's base 2. It's made up of, it only has 2 digits to work with. You got 0 and 1, 2 total. So if you're in binary land and you're trying to add 1 to 1, there is no digit for 2 by itself. You have to use a new place. 1 plus 1 in binary is 1, 0. That's 2. Isn't that cool? We liked to make things a bit shorter. So when you, instead of saying a digit in binary, a binary digit is called a bit. They took the B and they took the IT. That's a 0 or 1. And then 8 bits make a byte. Maybe we've heard of that before. Okay? So for example, here is 101101 base 2. This is a 6-bit number. 6-bit number. And a byte is just 8 ones or zeros. 1101. This is a single byte. I'll tell you what this means next time, but that's the idea. And then finally, remember the subscripts, because this is decimal. This is 1010. In binary, this is the number 10. the decimal number 10. They're not the same, and so I'm going to use that subscript to differentiate. It's a much smaller number when it's in binary because there's not as many digits to work with. Okay, so we're going to continue with that next time, but that's where I want to stop today. So we've learned a lot. See you next time.